Hello everybody. In this video, we're going to start with the solution of heat exchanger problem to get to understand how we can do that using Aspen Plus. We will go in multiple steps. We will first in this video go for the shortcut method, and we will see what kind of information we will provide and what kind of results we will get out of the simulation. And then next video, inshallah, we're gonna do the rigorous calculations just to see what is the difference in the outputs and what can we get out of it. So the problem that we are gonna solve is heat transfer or heat exchange between ferrione, which is the dichloromethane, which is a very famous refrigerant and coolant. We have flow rate of 12,000 kilograms per hour. The temperature is 250 Kelvin and the pressure is 8 atmosphere. And we want it to reach 300. So we are heating it, increasing the temperature by 50 degrees. And we are using ethylene glycol available at 370 degrees Kelvin and 3 atmospheres. We know that the minimum temperature approach is at least 15, which means that this temperature must be at least 15 degrees higher than this temperature. And this usually a parameter that's set in heat exchangers to make sure that the driving force is enough, so we don't need to use a very large area of heat transfer. And we know that this is the type of pipes that we're going to use, and this is not going to be a piece of information that we're going to use today or in this video. And this is the allowable pressure drop. Again, this is not an information that we are going to use today. So let's go to Aspen Plus and see what we have. So just to save some time, I have already defined the components, the ethylene glycol and ferrione, and I use the NRTL method because they're polar components. I have already defined the information or put the information that I have, so I know that the ferrione is 1200 kilogram per hour. It's 12,000 kilograms per hour, 8 atmosphere, 250 Kelvin. I think it is something. This is the mass fraction. This is the mass fraction of ferrione. And for the ethylene glycol in, I know that 350 Kelvin, this is mass fraction. This is 1, and we know 3 atmospheres, so we don't know the flow rate of the ethylene glycol that we are using, and this is going to be a point that we're going to discuss in few minutes. So these are the information that I have that I already defined here. I don't know, or I didn't define the temperatures of the exit streams because this is something that we are going to do when we define the heat exchanger itself. So this will be calculated based on the definition of the heat exchanger. Um, so now let's see what kind of information or what kind of blocks that we have that can be used to do the heat exchanging. So we have here 4 categories. This is what's called heater. It says thermal and phase changer, models heaters, coolers, condensers, etc. This is the heat exchangers. It's two-stream countercurrent or co-current exchanger. So just to understand the difference between these two, this is more concerned with one stream to adjust its temperature and pressure. So, and that's why when you open the options here, you'll find that there are different things that do not relate to heat exchanging or heat transfer. Actually, it's like a pump, like a valve. And the reason is of that is that first we cannot connect more than one feed, so it's more concerned with one feed stream. It doesn't matter what is the other stream that we're using to cool or heat, so it's just this stream. And the information that you won't need to provide are very simple. It's just the temperature and the pressure. It can provide or it will give you the duty that you need to achieve this heat exchange, and that's all. That's what you're gonna get. So it's doing flash calculations. That's why it doesn't matter what the other float is. and we're gonna use it in the next or the video after next, because there is one detail that's nice to know about Aspen Plus when we deal with this. The second type is the heat exchanger, and this is the one that we're gonna use. And you see here there are many types and many shapes of the heat exchangers. I personally do not know all of them. I know some of them, but there are like a lot of shapes. I think it depends on how the flow is arranged inside the heat exchanger. So if anybody is interested, you can go to the documentation or search online to understand what are the differences between these shapes. But the one that we generally use are these four, which are doing the same thing actually. This is called the simp, which is the simple shape, and this is the gen, which is the general shape. Again, this is the simp, and this is the gen. We have two of each, and this is a point that's pretty important. That we have simp HS and this simp HT. This is gen HT and this is gen HS. So we need to understand what is the difference between HS and HT. The HS is the hot. The H stands for the hot fluid, and S stands for shell. T stands for tube. So when you choose this heat exchanger, this means that you are choosing the heat exchanger where the hot fluid is routed in the shell. And by doing this, you have to make sure that the hot fluid is connected to the shell side. Otherwise, you will get an error while working. And this is what we were discussing before about the routing of the fluids in the heat exchanger. And we need before we choose one of these two to understand which fluid is gonna flow in the shell and which will flow in the tube. So let's take another look at the givens. So from the pressure we have this Freon is at higher pressure, which means that we need to route it in the tubes if we are looking at it from the pressure point of view. The two fluids are not corrosive, they are not fouling or not make a lot of fouling. So maybe one more parameter that we can think of before that, we don't know the flow rate of this stream, so we don't know which is the higher flow rate. But the point that might be or we can use is the viscosity. We stated that the viscosity or the high viscous fluid should flow in the shell. To figure out which fluid has higher viscosity, I would go to the components and review. We can find some information about the physical properties of the fluids from here. But if we take a look at these parameters, we'll not find the viscosity among them. And this means that I have to find it myself, or not myself, I mean do one more step. So we will go to pure component analysis and go to the flow, the transport properties, and we'll find that this is the mu. And this is the two fluids, and we will run the analysis. I don't actually care about the temperature, I just want to know which is more viscous. And from this you'd see that the liquid ethylene glycol has higher viscosity. It's way higher than the viscosity of Freon, which means that the ethylene glycol is better to be routed in the shell. And this agrees with what they said before, because we said that the Freon will be in the tube, so this will go in the shell, which is great. So I'm gonna pick the heat exchanger that has the hot fluid flowing in the shell, which is this. And now we can connect this into the tube, and it's telling that this is the cold fluid, by the way. It says cold required. Again, we will connect this ethylene glycol to the feed and or to the shell and get this out of the shell from the other side. And that is all we need to do for the connections. Now we should just go into the heat exchanger and see what information we need to provide. So when we double click on it, you will see that it is first asking what is the model fidelity. It is asking if you want to do shortcut calculations, you want to do shell and tube or kettle, thermosiphon, air cooled, or whatever. I'm sorry. So all of these are rigorous calculations, and this is the only shortcut method. So we will go for shortcut for this video. Here it asks you where the hot fluid will flow, either in the shell or the tube. And this is actually not active because I've already chose this when I chose the heat exchanger type that has the hot fluid in the shell. Now we will go to this. It's asking is in case of shortcut calculations, do you want to make the calculation based on counter current flow or co-current flow or multipass? I'm just gonna go for counter current for now. And these are the information that I want to provide for this part. Now it's asking about the calculation mode, how it is going to do the calculations of the heat exchanger. Either to go for the design. The design means that the program will select the geometry to achieve the temperature or the heat transfer that you are interested in. In the rating, it's different. You will provide information about the temperatures and about the area of heat transfer and the heat transfer coefficient, so that you can check if the specs of the heat exchanger are enough to achieve this heat transfer that you are interested in or not. So you're expecting in this case that you would get suitable or not suitable. This is the output that you get. For the simulation, you are not asked to provide any information or to not provide the information about the exit temperature, but you need to provide information about the heat exchanger itself, the exchanger area, the heat transfer coefficient, and the temperature approach. And it's going to do simulation and calculate the temperature that is coming out of the other side. And finally, the maximum fouling. It's like rating, but in this case, you are not checking if it's suitable or not. You are checking or trying to know how much fouling is allowable using this design that you are or the specs that you're providing. In our case, we are interested in design. We want the cold stream outlet temperature to be 300 Kelvin. And the temperature approach we set to be 15 Kelvin. And this is all what we need to specify so that we can get the heat exchanger running. If you press next, you'll find that it is not doing the simulation because there is one more piece of information missing, which is the flow rate of the ethylene glycol. And to get the flow rate of the ethylene glycol, let's take a look here. The flow rate of the ethylene glycol would affect this temperature. So very high flow rate will mean that the delta T will not be high, because the Q, think about it as an equation. The Q equals M multiplied by Cp multiplied by delta T. So as you increase the M, the delta T will decrease for the same Q. So the delta T means that this temperature will be high. It's 370, would be 360, 350, whatever. If the flow rate is low, then this will be or the delta T will be higher, which means that this will be low. So I need to put a value that will achieve the 315 degrees Kelvin that I want to achieve. And now let's see how we'll do this. Based on these values, I can kind of predict how much flow rate I would use, and this is according to the CP or the values of the heat capacities. I know the Q equals this flow rate multiplied by CP of the Ferrion multiplied by this delta temperature, which is around 50 degrees Celsius. And the same here, it is M, which I don't know, multiplied by Cp, which I don't know, multiplied by the Cp, which is around, or delta T, I'm sorry, which is around 50. It's 55 degrees. So the delta T is almost the same. And from this, I can tell that the ratio between the flow rates would be inversely proportional to the ratios of the CPs. So if I can get a sense of the ratio of the CPs, I can find or use a number that is logical for the flow rate. So to do this, I can repeat what I did before, but instead of doing it for mu, I would do it for the CP of the it's not here, it's the ideal gas. It's not the ideal gas. I want the CP Okay, let's go for it just to get a sense of the numbers, and then we'll see. So from this we can tell, or no, it's not the right thing actually, because it's a gas. I don't want it to be a gas, so I'm gonna use maybe I can find it here. It is CP of pure component. This is what I want to do. And from the analysis, I can tell that for the temperatures, I'm going up to 350, so I'm working in this range. So for this range, the CP for ethylene glycol is almost double the CP of the Freon. So this is an important piece of information, and from this information, I can tell that if the CP of ethylene glycol is double, then the flow rate would be almost half. So it's gonna be 6,000. Just a number to start with. This is mass, and this is 6,000 kilograms per hour. So now I can the required inputs are complete, and I can run the simulation. And from simulation, now it's calculating. Now the results are available. One thing that we need to keep in mind is that the heat exchanger will you'll find that there are a lot of results here. It's not just one result folder like we're used in other units. You'll find that there is thermal results, which tells what are the temperatures. So the inlet temperature is 350 Kelvin, the exit is 305. So it's not actually achieving the temperature approach that we are interested in. Um, the pressure didn't change because in the shortcut mode we do not specify any change in temperature. This temperature is 300 as we requested, so it did what I want. In the exchanger details, it gives us about information about the duty, the area that I need for the heat transfer, the average U, and the U multiplied by A, and the LMTD. So it's giving me pretty much good information about the heat exchanger. It gives There are no information about the geometry. There are no information about the shell and tube results. There are no information about the air cooler. So for all of them, I don't have any information because in the shortcut mode, these are not information that I can get out of the this block as a result. So now let's go back. I just want to check something because I feel there's something wrong about the numbers. This is 12,000 kilograms per hour, 250 Kelvin, and this is ferrion. This should be okay. And now let's see the other stream. 6,000 kilogram per hour, 350 and 3 atmospheres. Anyway, okay, so it looks okay. Um, oh, it's 370. Yeah, that's why. This is why I think the results are not right. So again, back to the third. Yeah, okay. This sounds good. So these are the outputs that I have. So there is one last thing that we need to do is to change the flow rate so that we can get this 315 as we want. And to do this, we can simply decrease the flow rate of the ethylene glycol and see how this will affect the exit temperature. But this is gonna be like a time-consuming thing, so we can simply do one other or use one other feature in Aspen Plus that we used before, which is the design specs. We have already used it in the flashing, if I recall right. So in this case, we have a parameter that we change to set another parameter. So the parameter of interest that I am interested in finding or achieving a specific value of is the stream variable, which is the the stream variable, which is the ethylene glycol out, and I want it to be I want the temperature in Kelvin, and here I would set the parameter, which is temperature, to the value of 315 and the tolerance 0.01, and uh, now let's see, the manipulated variable that I'm gonna change is the stream. Oops, the stream variable. and this stream is the ethylene glycol in, and the variable is the mass flow rate. And I know that I want to go lower than 6,000, so I'm gonna start with 4,000 for instance, up to 6,000. So these are the parameter, or the what I need to do. So now I can run the simulation, and it's now solved. We can see here from the results that the manipulated started by 6,000 and the temperature was 326, and it changed it to 44,780, and the result is 315. So now it's using this value to operate the heat exchanger. So for instance, if you open the stream results of the heat exchanger, you would see that the flow rate is 4,780.36, although it still keeps the input that I have here as the flow rate of the ethylene glycol to the 6,000. So this other number that I got from the design spec is overriding this number. It didn't change it because I didn't change this value from here, but it is using this new value as the value of the flow rate that is entering the heat exchanger. So this is all for this video. In the next video, we'll see how we can shift to the shortcut method, or from the shortcut method to the rigorous method, and what outputs we can get out of the rigorous method. So I'll see you then, inshallah. Goodbye.